Already and okay.
Sure.
All right. So welcome back everybody to the last talk of the day and indeed of this meeting. Very pleased to introduce Taboka Chalebgwa, who is going to talk to us about an algebraic independence result for Euler factorial series. Please, Taboka.
All right. Thank you, Margaret, and thanks to the organizers for organizing the conference and also giving me an opportunity to take part in the program. So this will be I'll be talking about a problem that sort of recently cropped up in our joint work with Andrew Raven and Chandra at Stellenbosch University. So, and thanks to everybody for coming along. I know that apparently today it's the International Logic Day, so you may have knowingly or unknowingly decided to come to the one talk of the day that does not use logic. But thanks. Maybe I should have saved that for later. But, all right, let's see. Perfect. So let's just quickly briefly recall a couple of results that will sort of guide our subsequent discussion. So I'll remind you of the Hermite-Lehmann theorem, which just says that whenever alpha is a non-zero algebraic number, then the exponential of alpha is transcendental. Or another way of looking at it is that if you do not assume that alpha is algebraic, whenever alpha is a complex number, then at least one of either alpha or e to the alpha will be transcendental. And then, of course, there's the generalization of that, which is the Lehmann-Weierstrass theorem, a classical theorem in transcendental number theory. So for that one, it says that if you have n algebraic numbers that are q-linearly independent, then the n exponentials will be algebraically independent over q. And of course, there is the notorious and classical Schindler's conjecture, which just tells us that, which does not assume algebraicity of the n linearly independent complex numbers. And then it says that if you just have n linearly independent complex numbers, then at least n of the two n numbers that you get from exponentiating your original tuple, at least n of those should be transcendental or algebraically independent further. Right. So a sort of meta observation or meta guiding principle for our discussion, I sort of decided to summarize it as a functional Lehmann-Weierstrass theorem together with a Zegel-Szydlowski theorem should result in a Lehmann-Weierstrass theorem. And I'll explain now, put a bit of meat on that skeleton, and let's see if this is convincing for us. So what would I be referring to when I say a functional Lehmann-Weierstrass theorem? Well, this would be a theorem of the sort. Suppose you've got some transcendental function or a formal power series satisfying additional certain criteria. It may be criteria on their coefficients, maybe criteria on certain differential algebraic properties of the functions. But suppose you just have some transcendental function, and suppose you have a result of the form, whenever you have n linearly independent polynomials, then the n functions that you get by composing your original function with the polynomials will be algebraically independent over some function field, for instance. So that's what I would mean by a functional Lehmann-Weierstrass theorem. Of course, you can sort of see how it relates to the classical Lehmann-Weierstrass theorem, which is the arithmetic version of that. And of course, I've used an arbitrary function here, not necessarily just the exponential function. And then what would I mean by a Zegel-Szydlowski theorem? And we'll take a closer look at one of the original Zegel-Szydlowski theorems in a bit. But in the meantime, so suppose for the very same function that you had in your functional Lehmann-Weierstrass theorem, now you have a result that says if you have n such functions, so to speak, belonging to the family of F, sharing the properties that we delineated, defining F. Suppose you've got n of those functions. Now, if you have a result of the form, whenever those n functions are algebraically independent, and in addition constitute a solution of a first order system of linear DEs, then when you evaluate those functions at an algebraic number, which is of course not a singularity of the system, then the resulting n algebraic numbers are algebraically independent. So that is a typical statement of the Algebraic theorem. And so the observation here might already be obvious now, is that if you've got these two theorems, then you should be able to immediately deduce Lehmann-Weierstrass theorem for your function. So that is more specifically, how do you go about doing that? So suppose you start with n linearly independent algebraic numbers, and then in the functional Lehmann-Weierstrass theorem, in the space of your g's, g1 to gn, you just define them to be alpha z, and then your functions f1 up to fn that are appearing in the Chalebgwa theorem, just define them to be f of alpha z. Now, by the functional Lehmann-Weierstrass theorem, since these polynomials are linearly independent, what they then deduce is that your functions are algebraically independent. And then by the Chalebgwa theorem, since now you have got these n algebraically independent functions, if you evaluate them at 1, say, then the resulting n numbers should be algebraically independent. So in particular, whenever you have n algebraically independent numbers, what you then get is that f of alpha 1 up to f of alpha n are algebraically independent. So this is a type of a Lehmann-Weierstrass theorem for your given function. Now, so where does the Chalebgwa theorem come from? I would say perhaps it came from a question of trying to, whenever you're given a transcendental function, when can you ensure that it takes transcendental numbers at algebraic inputs? So the Chalebgwa theorem sort of answers this question in the sense that you can impose certain conditions on your function, including imposing certain arithmetic conditions on the coefficients of the Taylor series expansion of your function, and a few other conditions, but that will give you what you are looking for. And in particular, there is what's defined as the Zegel E functions, and they are just an abstraction of the exponential function. The quintessential example of an E function is the exponential function, and I think one of the Bessel functions as well, for those who are familiar. Now, essentially, you suppose that the coefficients of your power series come from an algebraic number field of a finite degree, and then what you then do is you impose growth conditions on the coefficients of the function, basically. So the coefficients of your function together with the algebraic conjugates. And if you have a function for which satisfies these conditions, then we would say it is a function, essentially. Now, the Chalebgwa theorem says that whenever you have n E functions that are algebraically independent and they form a solution of a system of first order linear differential equations, if you plug in an algebraic number, which is not a pole or a singularity of any of those functions, then the n numbers that result are algebraically independent. That is a translation of the technical statement that we see in front of us. Now, in line with our meta observation, there are several different ways of showing that whenever you have alpha 1 up to alpha n being linearly independent complex numbers, then the n functions e to the alpha 1 up to alpha n are algebraically independent over CC, sort of different ways that one can approach this question, but sort of a classical question, and it can be shown. And then, which means whenever you impose that in addition your alphas are algebraic numbers, then you can apply the Gauss-Shidlovsky theorem to them and then immediately deduce the Lin-Weierstrass theorem, similar to sort of the meta theorem that we saw in. Okay. Now the question is, one of the questions would be, what about the p-adics? That's sort of what we wondered about. And so the p-adic Lin-Weierstrass theorem for the exponential function is so widely open. There are some nice results by Amber Dalu, but it's still open. And but at least there's a nice result by Moller in 1932, where the analog of the Helmut-Lehmann theorem for the p-adic exponential is proved. So at least the Helmut-Lehmann version is known. But unfortunately, Moller's methods do not extend to the Gauss-Shidlovsky theory, because otherwise, if that were the case, then one would sort of just use that meta approach and then be able to immediately deduce the p-adic Lin-Weierstrass theorem. So it's a little bit difficult to actually get a Gauss-Shidlovsky theorem. Well, we don't have a Gauss-Shidlovsky theory for p-adic exponentials. That's pretty much the case. But if one is not hung up on using the exponential function itself, something could be done, something could be said, although it's still, as we'll see, it's still very far from a classical Lin-Weierstrass or Gauss-Shidlovsky kind of theorem, but at least in the same spirit, you could say something that is reminiscent of what we just talked about. So we'll be considering the Euler factorial series, which is the function that you see in front of you, and factorial z to the summation of that. And of course, this only converges at 0 if you consider it as a complex analytic function, but it has a positive non-zero finite radius of convergence if you consider it as a p-adic analytic function. And so I've got, say, two facts there in front of me. So it converges, it has a positive radius of convergence in CP, and it also has its own nice little algebraic differential equation that it satisfies, in case you're curious. And then now, instead of, I mean, an ideal situation, I guess, would be if I were then to tell you confidently that we are able to deduce a Lin-Weierstrass theorem for this particular function, but it's also a little bit difficult to try and tackle it directly that way. So then, what is known so far about this function, at least in the direction of the Gauss-Shidlovsky theorem, requires a little bit of preparation in terms of definitions. So in this case, suppose you have an algebraic number, and then of course there are certain convergence issues that one has to bear in mind. But suppose you have an algebraic number, and then for that algebraic number, e to the alpha, say it converges in all but finitely many primes. So that should not necessarily hold all the time, but for many other algebraic numbers, that does happen. So suppose you're in that case, then in this case, we naturally identify e to the alpha with an element of the direct products of these fields, CP, for all primes P, or for the primes for which e to the alpha converges in CP. So by a natural identification, I just mean that each nth or pth entry of alpha just corresponds to the value of E of alpha in the corresponding periodic field. Now, given that, so at this level of direct product of rings, we can use a slightly different version of what we need for such an element to be algebraic or transcendental even. So essentially, we'd say such an alpha bar is algebraic if you can find a non-zero polynomial with rational coefficients such that that polynomial is zero at each entry of alpha bar. Then we say it is algebraic. And think, for instance, of maybe a repeating sequence, essentially. Maybe you've got a sequence that repeats at times, periodic sequence of that sort. And then, of course, you can just form a polynomial whose zeros are those numbers, and then you get such an example of such a number. And then you then say alpha bar is transcendental if it is not algebraic. And in particular, we say it is infinitely transcendental if for any non-zero polynomial, there are infinitely many primes for which P of alpha P is not zero. And then if you've got n of these alpha bars, you analogously define the notion of infinite algebraic independence. So just replace x with x relative to xn in the definition of infinite transcendence. And so armed with these definitions of algebraicity and transcendence, or rather before we get to that, one thing that one should maybe highlight at this point is that an infinite transcendence does not necessarily mean element-wise transcendence of those elements. So you can sort of see how far we are with sort of understanding that any particular input is algebraic or transcendental. But in any case, for example, if alpha is 1, 2, 3, then it is infinitely transcendental, an example of an infinitely transcendental element. Well, because in any case, any polynomial has finitely many zeros only. So, all right. So as an aside, just in the theory of this F function in particular, so this Euler factorial series, it is still an open problem whether, say, e to the minus 1 is irrational or even non-zero. Yeah. But just what's known, Chalebgwa has proven that e to the 1 is, or e to the plus or minus 1 is not zero for infinitely many primes. And that's sort of a whole other direction of research. But in the direction of Chalebgwa, he's also proved a rather interesting Chalebgwa type result. In this case, we look at a slight generalization of the Euler factorial series, where we also impose conditions on the coefficients of your function. So the F series or F functions are defined sort of in an analogous manner to how we saw E functions being defined by imposing certain arithmetic restrictions on the coefficients of the functions. And then, but in such a way that, of course, you are considering them over periodic fields. In this case, a Chalebgwa type result for well, Chalebgwa obtained a Chalebgwa type result for this F series. And essentially, it says that if you've got n such F series, whenever they are algebraically independent, formally over CZ, then the numbers that you get by plugging in an algebraic number that is not the singularity of the system will be infinitely algebraically independent over Q. So that's a Gaussian-Westy type theorem for these functions. But of course, with the caveat here being that we have to bear in mind we're talking about the infinite algebraic independence and not just algebraic independence in the conventional way. But then that's, once we sort of get to that point, we still wonder whether we can use our meta theorem to deduce quote unquote a Lindman-Weierstrass theorem, corresponding Lindman-Weierstrass theorem in this case. And that immediately results in, essentially, because we already now have the Gaussian-Lofty side of this, what one would need is to sort of just basically answer the problem number one. That's right. If you have n linearly independent complex numbers, the functions e to the alpha 1 z up to e to the alpha n algebraically independent of CZ. And if one shows that, then you will immediately get a corresponding Lindman-Weierstrass type result for these functions. And so, and for this particular problem, it's actually not too difficult to obtain it, just pretty much using more or less as formal algebraic arguments and without recourse to even the analytic properties of the B functions. I know in the abstract I promised to talk a little bit about the p-adic Levan-Miller theory, but essentially what I would say is the p-adic Levan-Miller theory kicks in if you want to tackle a slightly more general version of this result, where, because this is, we sort of conveniently set this up so that it would immediately give us what we want. But if you were to consider a slightly more general version of this problem, where these inputs here are not necessarily just these linear polynomials, if you just consider arbitrary functions or arbitrary general polynomials, then you need to use the growth properties of both the E function together with the functions that we are treating as inputs. In particular, you have to show that they have to deduce results about the Levan-Miller characteristic of a function together with, or in comparison with the Levan-Miller characteristic of that function composed with some other function, and then use asymptotics in the p-adic plane to show that a polynomial in these functions cannot be identically zero, meaning that they should be algebraically independent. That's sort of a general approach. But like I said, sort of just this case that is convenient to be applied immediately. This would be just elementary argument. And then it also turns out that there is what I would call a vertical version of a Gaussian-Lofty type result for these E functions. In particular, well, the horizontal version would be one where you just have this E function, and then you've got what you are varying that are the inputs in terms of alpha 1 z to alpha n z. A vertical version of the Gaussian-Lofty theorem would be where you fix the E function, and then you just look at the first n derivatives of that function. It also turns out that if you impose certain conditions on the coefficients of your function, you can get an algebraic independence result or Gaussian-Lofty type result for E functions together with their derivatives, essentially. And so problem number 2 would just be to show that for this Euler factorial series in particular, the function together with its -1 derivatives are algebraically independent. And once you've established these two theorems or problems, you immediately get a result of the sort given alpha 1 up to alpha n algebraic numbers, then the Wronskian of E1 up to En is has full rank for infinitely many primes. That's sort of what you deduce immediately, because what you get is that each for all of the matrix of the Wronskian is algebraically independent, and each column is also algebraically independent for infinitely many primes P. And so I will stop here, and I'd like to say thank you for coming to the talk. Apparently today it's World or the International Logic Day, so thanks for coming to the one talk that does not have logic. All right, I'll stop here.